In today's video, we'll be diving into the world of chemistry and exploring Red 3, also known as erythrocene. In case you've been living under a rock, Red 3 was banned this week in the US. You've probably seen it in your favorite foods, cosmetics, and even some medications. But what exactly is Red 3? How is it made, and why do some people worry about its safety? Let's break it down. First things first, let's talk about the structure of Red 3. Chemically speaking, it's a synthetic dye with a molecular structure built around a xanthine backbone, which consists of a fused tricyclic system that includes both benzene rings and an oxygen-containing heterocyclic ring. The structure of Red 3 is modified by the presence of 4 iodine atoms attached to the aromatic rings. These iodine atoms are key to the dye's bright red color and stability. The iodine atoms increase the conjugation in the aromatic rings, which is crucial for absorbing light in the red region of the visible spectrum. The dye is generally used in its sodium salt form, which enhances its solubility in water. This solubility is important because it allows Red 3 to be incorporated into aqueous solutions, making it suitable for various industrial applications, including food and cosmetics. The molecule also contains carboxylate groups that ionize in water, forming salts and further increasing solubility. The overall structure of Red 3 is relatively stable due to the iodine atoms and the conjugated system of bonds in the aromatic rings. This stability makes it a durable dye that resists degradation under standard conditions, which is a significant advantage in both food and cosmetic formulations. The synthesis of Red 3 is a multi-step process that begins with the creation of the xanthine core. Once the xanthine core is in place, iodine is introduced to the aromatic rings through electrophilic halogenation, where iodine atoms are added at positions 2, 4, 6, and 8 to enhance conjugation and light absorption, giving the dye its vivid color and stability. After halogenation, sodium hydroxide or sodium carbonate is used to form the sodium salt, making the dye water-soluble. The final product is purified. Red 3 exhibits several notable chemical properties that make it effective as a dye and versatile in various applications. One of its most important properties is its ability to absorb light in the visible spectrum, particularly the red portion of the spectrum. This absorption is due to the extended conjugation in the aromatic rings and the influence of the iodine atoms, which help to stabilize the molecule. As a result, Red 3 produces a vivid red color, which is why it is so widely used as a colorant in foods, cosmetics, and pharmaceuticals. Another significant property of Red 3 is its solubility in water, which is a result of the formation of sodium salts. These salts dissolve easily in water, allowing the dye to be incorporated into aqueous solutions. This solubility is particularly important for applications in beverages, gelatin, and cosmetics, where water-based formulations are common. The dye also exhibits a degree of thermal stability, meaning that under normal conditions, it does not easily degrade. However, it can be sensitive to extreme heat or UV radiation, which may cause it to break down and lose its color intensity. Red 3 also shows some pH sensitivity. In acidic environments, the dye tends to exhibit a more intense color, while in basic conditions, the dye may lose some of its brightness due to shifts in the electronic structure of the molecule. This characteristic is important because variations in pH can affect the stability and appearance of the dye. Red 3 is widely used in several industries, primarily because of its vibrant color, water solubility, and stability in various formulations. One of its main uses is as a colorant in the food industry, where it is added to products such as fruit juices, desserts, candies, and baked goods. The dye is favored in these applications because of its ability to impart a bright red hue to the products, making them more attractive to consumers. In addition to food, Red 3 is also used extensively in the cosmetic industry. It's found in products such as lipsticks, nail polishes, blushes, and eyeshadows, where its solubility in water and stability make it an ideal colorant. The vibrant red shade it imparts is highly sought after in many cosmetic formulations, and its long-lasting properties ensure that the color remains stable throughout use. Red 3 is also used in pharmaceuticals for the coloration of tablets, capsules, and liquid medications. The dye's solubility and stability in aqueous solutions also make it suitable for use in liquid formulations. So, whether it's in your candy or your lipstick, Red 3 is doing its job of adding a vibrant red hue. Despite its widespread use, the safety of Red 3 has been a topic of considerable concern. The dye has been linked to potential health risks, particularly regarding its carcinogenicity. Some studies have shown that Red 3 is associated with the development of thyroid tumors in laboratory animals, leading to significant regulatory scrutiny. This potential carcinogenic effect is thought to be related to the iodine atoms in the dye, which could disrupt normal thyroid function. However, evidence of its carcinogenicity in humans is still inconclusive, and more research is needed to determine the full extent of its potential risks. As a result of these concerns, Red 3 is banned in food products in several countries, including the European Union, where it is classified as a potentially harmful substance, and now in the US. While Red 3 is generally safe in regulated amounts, it's best to be cautious, especially when it comes to long-term exposure. Red 3 is a synthetic dye that has been used for decades in various industries, including food, cosmetics, and pharmaceuticals. Its vivid red color, solubility in water, and stability make it incredibly useful. However, concerns about its potential carcinogenicity have led to increased regulation and scrutiny of its use. Ongoing research into its toxicological effects will ultimately shape its future use and regulation. As always, thank you for watching. If you have any video ideas, comment them below, and we'll see you in the next video.